theorems because it has like a James Bond sounding like name. The implicit Q theorem. Okay. So the implicit Q theorem says that we have two orthogonal matrices Q and V. And for notation purposes, we have a column partition, as usual, for Q and V. Okay. And H and G are both Hessenberg. And H is assumed to be unreduced. I'm not making a similar assumption about G. We assume that the first columns of these transformations, Q and V, are equal. Now, if all of these assumptions are true, the implicit Q theorem says that each of these other columns of Q are equal to the corresponding column of V, except possibly assigned. So they're scalar multiples of one another. Furthermore, the entries of H and G are equal, at least in absolute value. So they might have opposite sign. Now, a consequence of this is, because we're assuming that H is unreduced, G is also unreduced. And the terminology we use here is that Q and V are essentially equal. So the orthogonal bases we have are basically the same. We just might have a sign difference. So in other words, the reduction to Hessenberg form is uniquely determined by the first column. And when we get to the finer points of making these algorithms faster, that's really going to save us. Okay. Now, because I can never resist doing this, I can't help but at least step through a proof. Or at least the main idea of it. It's not even a difficult proof, really. Okay. So what I do is, so at least a sketch of a proof. Now, from this first Hessenberg reduction, I can rearrange it to isolate A. So that's Q, H, Q transpose. But I have my other Hessenberg reduction, D transpose A, B is equal to G. So I can take this expression for A and put that in here. So now I'm going to have V transpose Q, H, Q transpose V is equal to G. Now, I'm going to call this matrix W, so therefore this is W transpose. V and Q are both orthogonal matrices. The product of orthogonal matrices is orthogonal. So I can say that so W is orthogonal, and that means I can move this W transpose to the other side. I can say WH is equal to GW. Now, and I'm trying to get this relationship between G and H, and so I need to find out more about this W matrix to see what that relationship really is. So what can we find out about W? I'm going to go column by column. So the first column of W, well, I use the definition of W, that's V transpose Q E1. But QE1 is the first column of Q, so that's Q1. But Q1 equals V1. V1 is the first column of V. Right that way. V is an orthogonal matrix, so V transpose V is identity. So first column of W is just E1, the first column of identity. So it's 1 and then all zeros. Okay. Now I want to find the second column of W. And to get that, I'm going to look at one column of this matrix equation here. I'm going to look at the first column. So I take the first column on both sides. So I have WHE1 equals GWE1. But WE1 is E1, so I have that. Okay. Now, G and H are both upper Hessenberg. And I'm taking the first column of both. If I take a first column of a Hessenberg matrix, what do I know about that column as far as what's 0 and non-zero?
The first two rows are 0.
Yeah, only the first two rows
I'm
can be
not
known.
there.
Yes, and actually, from a case of H, we know that the first two entries, the second entry has to be non-zero because it's unreduced. So what I have here, I'll write this way. I have W1, W2, so forth, Wn. And then I have my first column of H, so that's H11, H21, all zeros. And then I have a first column of G, so that's going to be G11, G21, all the rest zeros. Okay, so now if I carry out the multiplication on the left side, I have H11, W1, but that's W1 is E1, plus H21, W2 is equal to this column G1 right here. Now, the only unknown in this equation is W2, the second column of W. So I'll go ahead and solve for it. So W2 is G1 minus H11 E1 over H21. H21 is guaranteed non-zero because H is unreduced. Now, what's the structure of this column? Again, in terms of what's 0 and non-zero. Which entries can be non-zero?
Okay, so G1, the first two entries are non-zero.
Yep.
And then you're dividing by non-zero. And then H11, and then you're subtracting off a non-zero. H1 on E, what times E1 though.
Right.
So that's only subtracting off the first one.
Yes.
So still the first two.
Yes, only the first two entries. So this is 1 over H21. We'll pull that out. And then we have G11 minus H11 here, and then G21 here, and the rest are all zeros. So let's think about this. The first column of W has only one non-zero entry, because it's E1. The second column has only two non-zero entries. if I continue, and this is where I say, by a simple inductive argument, what's going to happen to W? What kind of structure is it going to have? What?
Triangular.
Upper triangular.
Because the first one has just one.
Yeah, we have one non-zero entry here in the first column, then 2 in the second. Because Hessenberg, it'd be 2 and 3.
Because that's W2 that we just
Yes.
found.
Yeah, so what that means is W is upper triangular and it's orthogonal. From homework 1, the matrix is triangular and orthogonal. It is
Diagonal.
diagonal. And what else do we know?
Something about diagonal.
The diagonal entries are,
Yeah,
Also the eigenvalues.
well, they are anyway. We know a little bit more than that. No one remembers from that assignment?
Does it have more to do with the triangularity?
No.
No? You want to give us a hint?
Nobody? I think pretty much everybody in this room got it right. But
Can you give us a hint?
I just asked.
the numerical value of these diagonal entries.
Right.
Oh.
Or,
Negative.
yes, plus or
Oh.
minus
No,
1.
never mind.
Yes. So W is diagonal, and each diagonal entry is equal to plus or minus 1. And this is actually, this leads us straight to the conclusion we need because each diagonal entry is VI transpose QI. So that inner product is equal to plus or minus 1. Also, each V is orthogonal to all the other Q's. So they have a different index. So, so Wij, which is the inner product of Vi and Qj, is equal to 0 if I is not equal to j. So from these inner products being plus or minus 1, and these inner products being 0, that leads us to conclude that Qi is equal to plus or minus Vi. So it's enough to conclude that these vectors are the same except possibly for a sign. I'm running on the board here, but okay. Each entry of G is VI transpose A Vj. But each V is plus or minus a corresponding Q. So that's going to be equal to plus or minus Hij, because of the relationship between the V's and the Q's. So that's our conclusion. That's the implicit Q theorem. And yeah, I kind of glossed over the inductive part, but you get the idea. So we have this uniqueness, and wow, made use of a homework problem. So, how does that happen? Okay. So questions about the implicit Q theorem?
Is there a mistake in the notes then?
Yes, on
it's-
page 182.
I said, is there a mistake then?
Oh, where?
But right there it says in W inverse is equal to W transpose, which means it's lower triangular, and I thought we just said it's upper, or does it really matter?
Oh,
Should it just
well,
say
it
upper
should have to be
triangular?
both upper and lower.
Upper and lower? Okay.
Yeah.
I just,
Therefore diagonal.
okay.
Yeah. So no, there's no mistake.
Okay. Well, I didn't know. We only said upper, and then I got confused.
Oh, gotcha. Okay. Oh, I say it earlier.
Yeah, because, well, and then it says something about the inverse is equal to the transpose, and you jump back to the inverse is
Yeah.
also, okay, cool.
Okay.
Thanks.
You have a question?
So all this is telling us that for every A, there's only one H, there's just one unique Hessenberg matrix.
Well, except the thing is, uniqueness really is determined by the first column. So once you set the first column of your Q,
Then you're gonna
right. Yeah. And that's going to enable us later to